Hi, we're from Group 7, and we would like to present our result for Case Study 3, the Smart Interior Lighting and Space Utilization. So these are the group members. My name is Diva Primaputri.
My name is Dinda Raya Audrian.
My name is Virja Tabina.
And my name is Zedin Lutfi Ramadan Firdaus. So we'll start with the problem statement. So for context, the problem revolves around a house, which is a two-story house, and the settlers are a family of three, consists of a father, a mother, and their daughters. And the space the house contains with two bedrooms, one living room, one kitchen, and one bathroom. And here, within the focus of finding comfort within ergonomics and then light intensity and effectivity of the electricity used. And there are variables, of course, of these problems, which is the light intensity and also the activity spatial requirements. And let us decompose the problems first. So the breakdown problems are supposedly the needs of adequate lightings for certain activities such as reading, studying, and relaxing, and also the efficiency to prevent overuse of electricity when it's not needed. And we're going to go into the pattern recognition now. So basically, we can see a pattern, which is the flow of the activities done within the house. So for example, in the morning around 6 to 8 a.m., the daughter and the parents would leave the house for school, while maybe the mother would stay in the house for other activities. So there are certain rooms that won't require any necessary lightings, while in certain rooms it will require lightings and other spatial qualities. And also, let's say in nighttime, everyone is gonna be asleep. So there would be requirements for certain intensity of light, such as dimly lit room or maybe no lightings at all for the settlers to actually sleep within the house. And here we go for the data representation and abstraction. So here we tend to put the data and variables into a table. So here are the more of like a keywords we're going to use, which is the natural light, artificial light, and user activity. And we also include the unit for each variables, which is for lights, it's lux, and for artificial light, it could be watt, because it requires electricity, right? And for user activity, it depends on what kind of activity is done in the time being. And here's the diagram for the abstracted problem. So we have in the bigger view, a focus of three problems, which is the natural light, artificial light, and user activity, right? And we're aiming for efficiency, energy, and comfort. And what can be done is using right intensity, specific only when activities are done prior to the intended, required intensity.
Okay, next we go to the algorithm. Okay, can we go next? All right, so for this case study, the algorithm that I found the most suitable is the greedy algorithm. So based on the greedy algorithm, we were able to select the route with minimal total travel time for a lighting command and short route to reduce the activation time that can improve the energy efficiency. So if we look at the table, it shows that the travel time between room in seconds. So kitchen to toilet is 2 seconds, kitchen to living room is 5 seconds, and toilet to bathroom is 4 seconds. Now by using the greedy algorithm, I here use the example to find the fastest route from kitchen to bedroom. So therefore, the route will be kitchen to toilet and to bathroom. And the total time is 6 seconds. Next. Okay, next is the flowchart. So first, based on the flowchart system, we need to read the occupancy. If the room is empty, then we turn off the lights. And if it's occupied, then we load the mode based on the target brightness. So for example, here I add the for working, it's going to be 300 lux, relaxing 150 lux, sleeping 5 lux, and I add one more constraint, which is for auto, is 200 lux. And if the user override is active, then we use the target mode that is set by the user. Now, otherwise, if it's no, then we need to continue to auto. Now, before changing the light, we need to run a quick ergonomics check, which include bed, TV, and desk that shouldn't be facing towards the window. If the layout isn't okay, then we need to adjust the furniture angle. And when the layout is passes, then we need to measure the natural light next. Now, here, if the daylight is already made the target mode, then we need to turn off the light since we're utilizing the natural light. And if it's too bright, then we need to close or adjust the curtains. And if it's too dim, then we need to increase the light towards the target mode. And finally, we repeat this step for each room, since in total we have 5 rooms. So we need to repeat the flowchart for 5 times. Next.
And so this is the pseudocode for our case. So the first step 1 is the checking of occupancy or the energy saver. This is the fastest decision. It's the maximum energy saving moves of the system that it can make. And then step 2 is set the target or the comfort goal. If the room is occupied, the system must figure out what level of comfort is needed. Then step 3, check the ergonomics, the safety and glare check. This is a crucial step for long-term health and comfort. And then step 4 is daylight harvesting. Right? So this is where the system chooses the most energy efficient action using the available sunlight, or L. So if the sunlight, or L, is too bright, the system tells the curtains to close. This solves the glare problem and keeps the electric lights off. And if the light's too dim, the system calculates exactly how much light is missing from the target. It only tells the electric lights to turn on by that minimal amount, maximizing the use of free sunlight.
Okay, so for the big O, we analyze the complexity of our control system, and the controls check each room one by one during every cycle. It rates the occupancy and the user override and the light level, then decide what action to take. So for each of these action takes constant time, and so if we have n rooms, the total time grows linearly with the number of rooms, and that means the time complexity is O of n, which showed that the system is efficient and scalable. Okay, for this one is explain the formal definition of big O notation. We write is as f of n is less than or equal to c times g of n, and for sufficiently large n. And it means that as the input n grows, f of n doesn't grow faster than the constant times of g of n. And so g of n is basically the upper bound of f of n's grow rate, and that's why we use it to describe how efficient an algorithm of our system is. And for this chart, we can see how O of n compares to other types of complexity, like O of n grows steadily and faster than constant time, but much slower than quadratic or exponential time. And that showed that our system performance increased proportionally with the number of rooms, so it's still efficient even when the building is one.
So next we have the algorithm testing. We use sample data. The sample data that we use is sunny working session with 450 lux and 120 centimeter path. We use this sample data as like the toughest, worst case scenario that the system could run. So the variables are room or R, input values are 1, living room, office, meaning it's a room where furniture can be moved. The activity mode is, of course, working because it's working session, and the maximum target light needed is 300 lux. The natural light, or L, is 450 lux, which is intense sunlight. It requires current action. And then this is the occupancy. The system must run full automation, and the user override is also, it means the automation is running, and the paths clear is 120 centimeters. It means it passes the first ergonomic rule because it's larger than 90, and then the desk or TV is facing the window, which fails the ergonomic rule. And so this is the effectiveness and final output. So the comfort is achieved, and it's a success because the glare is eliminated and the light level is brought down to the 300 lux requirements by using the curtains. And then the energy efficiency is maximized because the system relies on curtains and natural light only, achieving 0% artificial light energy usage. And the ergonomics is also a success because the faces window failure is corrected, improving the user's long-term comfort and reducing eye strain. The final output is the curtains adjusted and furniture moved because the room is fully optimized without turning on any lights. And this is the steps.
Okay, that's all for our presentation. Thank you.